بسم الله الرحمن الرحيم. بنرحب فيكم في المحاضرة رقم 7 lecture number 7 في random variables and stochastic processes. اليوم بدنا نتكلم عن بعض ال operations on one random variable. So today's lecture is operations on one random variable. وكلامنا اليوم في ال operations we'll take first one operation اللي هي ال expectation. Expectation. What do we mean by expectation? Expectation is the process of averaging. So expectation is the process of averaging when we are talking about the random variable. So expectation of a random variable is the averaging of this random variable. And the operation is symbolically represented by the uppercase E with square brackets, and the random variable is inside. Expected value of the random variable X is equal to X bar. This is another representation of the average or the expectation, and it's equal to the integration from minus infinity to infinity, x fx of x dx. This is the definition of the expectation of x. So if you have anything inside the square brackets, it will be put here, x fx of x dx. This is the definition of the expectation or the average. We call it sometimes the average, okay? For discrete random variable, we know that for discrete random variable we have fx of x is equal to summation from I equals 1 up to n p of xi times delta of x minus xi. So you have deltas or values, deltas weighted by the probability of each xi that you have in the summation. So fx of x is something like this. We have this before when we talked about the discrete random variable. PDF and the CDF is the unit step functions. We know this. So if we take the expectation, this is the general definition of the expectation. So if we take the expectation, expected value of x, which is equal to x bar equals to integral from minus infinity to infinity, x times fx of x will take the discrete value, which is the summation from I equals 1 up to n p of xi, the probability of each value of x, times the delta of x minus xi, close the parenthesis, dot dx. So this is the expectation for a discrete value. Now I'm gonna interchange the summation and the integration. So we can say that expected value of x, which is equal to x bar, in the case of the discrete random variable, is equal to the summation from I equals 1 to n p of xi times the integration from minus infinity to infinity, x times delta of x minus xi dx. Okay, so this one here, x times delta of x, if we use the shifting property, using the shifting property of the delta function, we can say that expected value of x is equal to x bar equals to the summation p of xi times, this one will be evaluated at xi, so this is equals to xi from I equals 1 up to n. Just to put it in the decent form, it's equal to xi times p of xi from I equals 1 to n. So this is our expected value for a discrete. So for a discrete random variable, this is the expectation. Okay, let's take an example and see how do we evaluate the expected value. Let me take first a very simple example. Example 1, I have f of x going, let's say, from 0 to 10. So this is fx of x. Definitely this one will be 1/10, so that the area under the curve should equal to 1. And we need to find x bar, which is the expected value of x. So x bar is equal to the integration from minus infinity to infinity, x fx of x dx, and this is equals to the integration from 0 to 10, x times fx of x is equal 1/10 dx. So this is equals to x squared over 2, and you have 1/10 before, and this one is evaluated from 0 to 10. If you calculate this, this is 100 divided by 20, and this is equals to 5. So the average value is equal to x bar is equal to 5, and you can see that it is in the middle of, for a uniform random variable, this is a uniform random variable, and x bar is in the middle of the period of the random variable, so it is equal to 5. Okay, let's take another example. Example 2. Determine the mean value of the continuous exponentially distributed random variable. Fx of x of the exponentially distributed random variable is equal to 1 over b e to the minus x minus a over b for x greater than a, and 0 for x less than a. This PDF looks like this. This is at a, and this is fx of x, and the amplitude here is 1 over b. Okay, so this is the function, exponentially decaying function with this form. So this form here started at A, and this is the exponentially function. The amplitude at A, when you apply x equals A, so you have e to the 0, it's 1, so the amplitude is the maximum, which is equal to 1 over b at this point, at the point x equals A. Okay, to find the expected value, we go to the definition and we apply the integration from here from A to infinity, x times fx of x, which is 1 over b e to the minus x minus a over b dx. This is equals to, we'll take the constant outside. The constant is e to the a over b divided by b e to the a over b over b. And then you have an integration from 0 to infinity, x e to the minus x over b dx. This one here, this integration should be solved by parts. Solve the integration by parts. So I'm gonna let u equals x and dv equals to e to the minus x over b dx, sorry. So I'm gonna take x to be u, dv is equal to the exponent, function, and make the derivative du equals dx, and here you do the integration, so v is equal to minus b e to the minus x over b. Okay, maybe I have to just put it in, okay, x over b, e to the minus x over b. So here we have to multiply, take the minus integral, so the integration will be equals to e to the a over b times minus b x e to the minus x over b plus b integration e to the minus x over b dx from a to infinity. And we will continue solving the second integral. Now the second integral is an easy job to do. So our expected value of x is equal to e to the a over b times minus b x e to the minus x over b plus, now the plus with the integration of this one, so you'll have a minus b squared e to the minus x over b, and the whole thing is from a to infinity. Okay, so this one, when you apply infinity here, you have e to the minus infinity, e to the minus infinity, both are zeros, so you have a 0. Let me just put it in nice form. E to the a over b times 0 minus minus, so you have plus. You apply a, so this b times a, e to the minus a over b plus b squared e to the minus a over b. This is the lower limit of the integration. The upper limit of the integration are both zeros. So it's 0 minus, you have two minuses here, so you have minus minus, so this is plus. And you take e to the minus a over b with e to the a over b. This one and this one will cancel with this one. and you have b here that will cancel with the square and cancel with b, so you end up with a plus b as an average. So the expected value of x is equal to a plus b. Okay. So this is the how to find the average value of an exponential random variable Okay. Let's define the expected value of a function of a random variable. Expected value of g of x, where g of x is a function of the random variable, is also equal to the integration from minus infinity to infinity, g of x, which is the function inside the brackets, times fx of x dx. So whatever the function is, you apply it here and you find the expectation. Okay? So if x is discrete, random variable, then expected value of g of x will also equals to the summation from I equals 1 to n, g of xi times the probability of xi. Okay? Okay. So this is the expectation of a function of a random variable. The conditional expected value as a definition, expected value of x given b is equal to the integration from minus infinity to infinity, x times fx of x given b dx, where fx of x given b is the conditional PDF probability density function defined in previous lectures. You remember that we defined B in two different ways. One time we defined B equals x less than or equal b, and one time we defined b to be equal x greater than b less than or equal a. So we define this one and we find the conditional density, and we define this one and we find the conditional density also. Okay? As well. All right. So based on the expected value of a function of a random variable, let me define something based on the expectation, which is called moments. Moments, they are parameters or values that can be calculated regarding the random variable, but they have so many information inside them. You can take, let me just take an example. When we take an exam, if you are taking an exam, one parameter that you rely on is the average. You ask your professor or you ask your instructor, What is the average? So if your grade is below the average, then you know that your grade is not good. If your grade is above the average, then your grade is okay. Okay. The further the grade is from the average, higher than the average is, which means that your grade is excellent. If it's very low, far away from the average, then your grade is a bad one. Okay, so moments, something that related to the averaging, and we have two types of moments. Moments about the origin, okay, and in this case, the moments about the origin, here we have g of x, which is here, is equal x to the power n for n equals 0, 1, 2, 3, and so on. Okay? And we denote the nth moment by m sub n, where n equals 0, 1, 2, etc. And we define m sub n to be equal to the expected value of this g, which is equal x to the power n. And this is equals to integration from minus infinity to infinity, x to the power n fx of x dx. So this is the definition of the moment, the nth moment about the origin. The nth moment about the origin is the expected value of x to the power n. From here we can say that m0 is equal to the expected value of x to the power 0, which is equal to the integration from minus infinity to infinity, x to the power 0, which is 1, times fx of x dx. And this is actually the integration of fx of x from minus infinity to infinity, which is the area under the PDF, which is equal to 1. And m1 is equal to the expected value of x to the power 1, which is equal to the integration from minus infinity to infinity, x to the power 1, x fx of x dx, and this is equals to x bar, which is the mean that we know. So m0 is equal to 1, m1 is equal to x bar, and so on. Those are just two of those moments about the origin. Okay. The second type of, sorry, why did I put here 2? This is 1. 2. The second type is the central moments. Central moments, or sometimes we call them moments about the mean value. Moments about the mean. Moments about the origin, and those are the central moments. They are moments about the mean. And here we have g of x is equal to x minus x bar to the power n, and also n goes from 0, 1, 2, 3, etc. And you can see that we are, as if we are defining a new random variable by subtracting the mean from the original random variable. If you call x minus x bar as some y as a random variable, then y has the mean value from x was subtracted from it. So the new mean of this y will be equal to 0. And this is why we call it the central moment, or the moment about the mean. You are taking this from x bar and using the expectation. Okay. So instead of saying that or calling that m, we will call it mu. So mu represents the central moment, m represents the moment about the origin. So mu sub n is equal to the expected value of x minus x bar to the power n. And this is equals to integration from minus infinity to infinity, x minus x bar to the power n, fx of x dx. Okay? Okay. So we can see here that mu 0 is equal to the expected value of x minus x bar to the power 0, which is equal to the integration from minus infinity to infinity, x minus x bar to the power 0 fx of x dx. X minus x bar to the power 0, this is 1. So you have the integration from minus infinity to infinity under the area, or the area of under the fx of x, which is equals to 1. So mu 0 is equal to 1, but mu 1 here is equal to the expected value of x minus x bar to the power 1, which is equal to the integration from minus infinity to infinity, x minus x bar fx of x dx. So this is equals to integration from minus infinity to infinity, x fx of x dx plus, minus, x bar is a constant, so it goes outside, and you have integration from minus infinity to infinity, fx of x dx, and this is equals to x bar minus x bar, and this is equals to 0. Okay? Okay. One important parameter from the central moment is mu2. Mu2 is equal to the expected value of x minus x bar squared, and we call this as sigma x squared, and this is called the variance. So the variance is sigma x squared, while sigma x itself is called the standard deviation. Okay, so the standard deviation is sigma x, and the variance is sigma x squared. And mu2, which is equal to sigma x squared, which is called the variance, it has a special name. It is equal to minus infinity to infinity, x minus x bar squared, fx of x dx. Okay, so you have to find the average, apply this equation as a function, and find the expectation of x minus x bar squared. There is also another way to do it. Sigma x squared is equal to the expected value of x minus x bar squared. If you fold this one, we can, or expand it, you can say that this one is equal to x squared minus 2x x bar, or x bar x, it doesn't matter, 2x bar x plus x bar squared. So expand the expectation over the parameters inside. So this one is equal to expected value of x squared, which is the second moment about the origin, minus this one is x bar squared, the 2x bar expected value of x, plus x bar squared. This is a constant, and its expectation is itself. The expected value of x is x bar, so you have minus 2x bar squared plus x bar squared. So you have expected value of x squared minus x bar squared. This one is m2 minus m1 squared. So sigma x squared, which is equal to mu2, is equal, so mu2, the second central moment in terms of the moments about the origin, it's the second moment about the origin minus the first moment about the origin squared. This one is m1, which is equals to x bar squared. Okay. You can think of this as, this is the AC power, this is the total power, and this is the DC power. So the total power minus the DC power is equal to the AC power. We will see this in later, discuss it in later lectures, inshallah. Okay. I'm going to take an example to find the variance of the exponential random variable. X is the exponential random variable with fx of x equals to 1 over b e to the minus x minus a over b for x greater than a, greater or equal 0 for x less than a. So this is your density function. Find sigma x squared. We need to find sigma x squared. We already found x bar, which is equal to m1. It was equal to a plus b in the previous example. Okay, in the previous example. Okay, so to find sigma x squared, we need to find m2, which is equal expected value of x squared is equal to integration from a to infinity x squared 1 over b e to the minus x minus a over b dx. So we have to find the integral, or evaluate the integral by parts twice. Evaluate the integral by parts twice. So you do it the first time and then the second time, and you will find that m2 is equal to a squared plus 2ab plus 2b squared. I already did that, and I found out that this is the answer. Okay? And, all right. So we find this one, we go to this formula, and we find sigma x squared to be equal to m2 minus m1 squared. And this is equals to a squared plus 2ab plus 2b squared minus, between brackets, a plus b squared. So this is equals to a squared plus 2ab plus 2b squared minus a squared plus 2ab plus b squared. So this one will cancel with this one, This one will cancel with this one. So you have 2b squared minus b squared, and the answer is b squared. So sigma x squared is equal to b squared. Okay? So this is how you calculate the second moment. Of course, you can go to the definition, to the exact definition. You have x bar equals x bar equals a plus b. You can plug it here. X minus, between brackets, a plus b, the whole thing squared. Use fx of x. Do this one directly, and you get the answer. But we usually find this way. This way is easier to find the variance or the second moment about the mean or the second central moment. With this, we end this lecture. Thank you very much, and we'll see you in the next lecture. We will talk also more about the expectation and the moments in the next lecture, when we talk about the characteristic function of the PDF and the moments generating functions to generate moments about for the PDF. Thank you very much.